So I will tell you about some of our recent advancement that we have been working on in my group. But before starting, I'd just like to take a moment of reflection. We're studying molecules, materials, and we are very lucky because we can work with colleagues all over the world, speak the same language, be friends, while a lot of horror is going on in the world. So I'm very thankful for being here with all of you, wherever you are. So let's try to introduce a little bit the motivation for this work. So in my group, we're interested in studying systems, which I like to call under the umbrella of systems phenomena related to sustainable energies. And for example, here on the left, you see, for example, a material like silicon vacancy. On the right, this is a metal organic framework where there can be electrocatalytic processes. And so we work on some and similar phenomena, and the challenge here is that these are systems containing transition metals, maybe radical species. So to perform electronic structure theory calculations, sometimes we have to go beyond the workhorse of electronic structure theory, which is density functional theory, and use multi-configuration wave function based methods, because these are strongly correlated or multi-reference systems. However, these methods are effective, efficient only for small systems because they suffer from the exponential scaling of full CI. So our long-term goal is to develop these methodologies, multi-configurational methodologies for extended and strongly correlated systems. And historically, in my group, we have been working with wave functions based on the active space concept. And so I'm sure this audience is certainly familiar with this concept, but for those of you who are less familiar, the idea is to, for example, if you have a molecule in your HOMO-LUMO region, or if you have a material where you have the valence, a conductive band, instead of just saying, okay, my orbitals occupy my electrons occupy these orbitals in this static one-shot way, we take this window of orbitals and electrons and allow the electrons to occupy these orbitals in all possible ways. So you can think about a full CI within the active space, while the other orbitals are treated like in Hartree-Fock or Kohn-Sham. The problem is that you still have an exponential scaling with the number of electrons and orbitals that one has in the active space. So over the years, we have tried to develop methodologies that somehow could break this exponential scaling. And for example, we have worked with one of these concepts, and there are many of them, and we are not the only ones developing them, is the generalized active space approach, in which the user defines many of these boxes of orbitals and electrons, and also defines the rules for the occupation. So there can be intra-box, intra-active space excitations, or inter. And this is, for example, the generalized active space concept also used in the ORMAS method developed by Mark Gordon and co-workers. So today I'm going to talk about one of these methodologies that has been recently developed in the group, and this is mainly work by Matthew Hermes, and this is called the localized active space self-consistent field method. So the idea is the following: imagine you have an extended systems and you have pockets of strong correlations. So here, for example, let's say that you are looking at these double NN bonds, and you dissociate them, and so there is a strong correlation situation. And so you could really divide your system in different subsystems, real space localization to fragments, and build a wave function based on the active space on each of these subsystems. And then the last wave function is just a product of these fragment wave functions and a single determinant that is a sort of mean field that embraces the whole system. And so this allows us to basically use all the algorithmic features of density matrix embedding theory, and I will talk more about it later. But the idea is that one could have only one path for the active orbitals, and from this single determinant, only one receives the non-trivial path states, and one can decompose the last wave function like a single determinant. So in such a way, then the energy can be obtained by a variational optimization of the last wave function. And this method, which basically has this idea of breaking the active space into fragments and writing your wave function as a product of these localized active space wave functions, as maybe one can think, okay, it reminds us of GASSCF or LASSCF, but it's more approximate because you just have a product form of the overall CI wave function. And the beauty is that the exponential scaling depends only on the size of the local active space, but not, there is no exponential scaling with a number of subspaces. And this idea of LASSCF has similarities with other methods, for example, the active space decomposition proposed by Parker and Shozaki, or the mean field by Scuseria, and so on. So here, to show you how it works, again, let's suppose that you have this super system, and now we want, first of all, to set up a active space wave function on the left fragment. Let's call it the left impurity. So one freezes all the orbitals related to the right impurity, and then one does the same by freezing everything related to the left impurity and optimizes the right impurity. And then one optimizes the inactive orbitals, and this is repeated until stationarity is reached. And so, as I said, LASSCF uses the same algorithm as density matrix embedding theory. If there is time, I will say something about it at the end. But the idea, and there will be another talk about it later, is that in DMET, one classifies the system into a high level, which we call it the impurity, and then there is the environment. And through a Schmidt decomposition, one is able to set up a problem, or a wave function that has a size that is maybe twice as much as the size of the high-level wave function. And then in an iterative way, a minimization between the density of the mean field and the density of the high-level calculation is performed. And different high-level methods can be used. So we use the same algorithmic features for LASSCF. And now I want to show you some of the performance of this method. So here we are just considering a system where there is only a strongly correlated fragment, the one in the middle, which is this double bond, and we are breaking it. And so the other fragments are weakly correlated, just so you can think about them as forming this mean field. And here you see the energy as a function of the nitrogen-nitrogen bond distance. And the reference in this case is a CASSCF 4 in 4, the black continuous curve. And you see restricted artery Fock, unrestricted artery Fock, how miserably they fail. And then there are some flavors of density matrix embedding theory. One can be a single iterative procedure. One can be a iterative, so a single iteration procedure, an iterative procedure. And in general, I mean, even if DMET performs reasonably well at equilibrium, things become more problematic at large separation, where strong correlation becomes more important. On the other hand, our LASSCF 4 in 4, so it's the same as CAS-SCF in this case, it agrees with CAS-SCF, and this is reassuring. Let's look now at the case in which we have two of these strongly correlated fragments, so the one on the left and the one on the right, and we are dissociating them simultaneously. And here you see again, Hartree-Fock fails in all possible ways. DMET also fails, whether it's iterative or a single shot. On the other hand, CAS-SCF and LASSCF really agree. And here, LASSCF called 8 in 8 actually corresponds to two subspaces of 4 in 4 each. So this is quite promising. The reason why there is this good agreement is because these two strongly correlated fragments are well separated by a weakly correlated fragment where there is a carbon-carbon double bond. These are triple zeta calculations. Yeah. Now, this is another system in which the method is reasonably successful. So, and this is really where we are moving forward. So let's say that you have a system with a series of transition metal centers. This is a prototype with only 2 of them. And if one does a CAS-SCF and just wants to include the d orbitals on each iron, one would have to perform a CAS-SCF 12 electrons in 10 orbitals. On the other hand, we can set up 2 separated active spaces, 6 electrons in 5 orbitals on each transition metal. And with this approach, we have computed the relative energies of the 2 spin states, the singlet and the non-net. So according to CAS-SCF, and they should be degenerate, they are, and this is the number of Slater determinants corresponding to the singlet and non-net state with the CAS 12 in 10. And now here we have the LASSCF wave function. And the non-net, there is only one trivial way to obtain a non-net. You have an MS +2 on each iron atom. The singlet, there are various ways because LASSCF is not an eigenfunction of S square. And so here we are looking at these antiferromagnetically coupled quintets that overall give a singlet. And so this is the difference with respect to the non-net CAS-SCF energy, which is pretty small. And so the energy difference between the 2 states is 0. And here we have a significant reduction in the number of configurations or Slater determinants. So this seems quite promising. However, I mean, LASSCF is really this product of wave functions. So it works only when there is no strong correlation among these fragments. And so here I will show you a typical limitation of the method. Let's suppose that here we are still breaking these 2 nitrogen-nitrogen double bonds. However, we have an overall a system with a delocalization of a pi system because we have also a CC double bond in the middle. And so dividing up the system like this with 2 CAS wave functions in the 2 NN, you see whether we do a CAS-SCF 8 in 8 or 10 in 10, we see that the corresponding LAS, which is in green, I mean, agrees reasonably well at equilibrium, but at dissociation, even if the shape of the curve is correct, it does not reproduce the CAS-SCF because, I mean, there is strong correlation here and we are totally neglecting it. Another problem of LASSCF is that, as I mentioned before, it is not overall an eigenfunction of S square. So it is within each fragment, but not the total wave function. And so, for example, these are 2 antiferromagnetic, so 2 states coupled in an antiferromagnetic way to a singlet, and these are 2 separate LAS states. So how can we try to improve upon it? So let's suppose, for example, that we are interested in J-coupling in multi-metallic systems. So usually, if you have two centers, A and B, the J-coupling can be calculated using this Yamaguchi formula, in which basically you take the difference in energy between high spin and low spin divided by the difference between the S square values for the two states. And if one wants to do a full LASSCF, this is prohibitively expensively, especially, for example, already you can do two metal centers, but when you start doing three, this is out of control. So the other thing that we should think about in this, let me just do one thing for a second. I want to remove this because otherwise I don't see. Okay, great. The other thing that we can do is, for example, if we think about dividing the active space into these multiplicatively separable subspaces, we could have, for example, a last state where we have antiferromagnetic coupling, or we could have a last state with the ferromagnetic coupling of the two states. And so the question is, could we compute J by taking the difference between these two, the energy of these two states? But the problem is that as I said before, LASSCF does not predict near-degeneracies in a quantitative way, because if you have these electrons in two different pockets, in two different subspaces, they interact only through mean field, and instead we need this interfragment interaction to get accurate values for J. So what the subsequent development on which we have been working is localized active space state interaction. And basically, one takes a set of these multiple LAS states and expresses the state interaction Hamiltonian in these spaces of states. And then the orbitals are averaged over all the states. And so the Hamiltonian can be diagonalized, and it will give this last state interaction I states as a sum of these states that form the basis. And so, for example, this is an example. Let's suppose that we have two localized doublets on two different fragments, and we can call these as neutral states. We can set up a state interaction Hamiltonian, which will have two of these states, so it's a 2 by 2. Or we can also consider charge transfer states, where the two electrons are all in one orbitals, and then we will have a 4 by 4 Hamiltonian matrix. And we can think that the neutral states basically describe what is called direct exchange between the two metals. The charge transfer states describe more the kinetic exchange. So how does this method eventually work? And before saying that, I'd say that of course, it depends on the choice of SI LAS states that one makes, but there are similar approaches in the literature. For example, one is pretty old, the interactive correlated methods, or again, the active space decomposition or rank one basis method. So let's look how LAS-SI works on these prototypical bimetallic compounds. So there are two chromium, they are 3+, and they are bridged through these OH groups. And these two D3 chromium ions are antiferromagnetically coupled one to each other. And so this coupling has been studied a lot computationally. And basically what has been shown in the literature, these are some of the relevant papers, is that really different methods can give different values. If one uses DFT, basically the intermediate spin states are not reproduced, not even qualitatively correct. So basically, what we can do is start considering some neutral LAS states in which we have these 3 unpaired electrons in each chromium, and they can be coupled in different ways. But we could also consider a charge transfer state. And so let's start by having on each chromium we have 3 electrons and 6 orbitals. And these 6 orbitals are just the singly occupied 3D and their correlating ones. So overall we'd have a CAS 6 in 12. And so these are the localized active orbitals on each chromium atoms. So 3 singly occupied D and the corresponding correlating ones for these 3D orbitals. And so let's see if one computes the LASSCF. So this is the LASSCF spin ladder and the J value that one obtains with this series of levels. And by the way, this value alone is not comparable directly to experiment, because one would have to do something on top of this wave function. So for example, perturbation theory or something else, and we'll talk about it later. But the idea here is that this is the CAS that we want to reproduce within the LAS framework. So if we do LAS-SI with only neutral high spin states, so not this charge transfer, we see first of all that the spin ladder is wrong. And J, of course, is positive instead of being negative. So the wave function are spin adapted in this case, but J is also qualitatively incorrect. And also with this approach, we only include direct exchange terms. Now, if we instead include also charge transfer states in our LAS-SI expansion, we obtain, first of all, the spin ladder becomes correct, and J is qualitatively correct compared to the LASSCF value. But also what is important is that besides the effect that whether J is qualitatively correct or not, when we include the charge transfer states, we have also this kinetic energy contribution to the coupling, and so we can quantify the various contributions, and we can say, okay, if the kinetic exchange is the difference between the total minus the direct, then we also know what the direct is, and we can quantify the contributions of these mechanisms. So this opens doors towards the opportunity of analyzing, for example, exchange, super exchange, changing metals, linkers, or the internuclear distances. So this is quite exciting. Another example that I can show you, let's say that we consider some conjugated species where there is an alternance of double bonds and single bonds. So we put each of these doubly bonded CC group within one fragment, and instead of having, an active space that is the sum of all of that, we just have, for example, 2 in 2 active space in each fragment. And so here you see, for example, if we have just the die-in, these are the number of configuration state functions for the singlet and the triplet, and this is LASSCF. And of course, the die-in is small, but as soon as we start going to larger chains, we see that these numbers really explode, while the LASSCF maintains, reasonable values. So these calculations are certainly more affordable than those. And let's see now. We are looking at the singlet triplet gaps for these polyns, and these are electron volt. I apologize that there is not the unit here. But you see, this is what LASSCF predicts. Now we do the various subspace decomposition. So the 4 in 4 for the die-in, we write it as a product of 2, 2 in 2, the 6 in 6 as a product of 3, 2 in 2, and then there are different ways in which we can partition the 8 in 8, either as a product of 4, 2 in 2, or as a product of 2, 4 in 4, and so on. And here you see the energy singlet triplet gap for LASSCF without any state interaction. I mean, the correspondence with CAS is not particularly good. And now what happens if we do LASSSI without charge transfer or with charge transfer? And we see that with charge transfer, the results agree pretty well with CAS-SCF, and eventually, I mean, these are, in order to compare to experiment, we would have to do something on top of this wave function, and I'm going to talk about it later. But in general, you can say that LASSSI is able to reform the bonds between fragments and delocalize these unpaired electrons over the entire molecule, even if we have decomposed it in subspaces. So to summarize this part of my talk, LASSCF, again, could be an efficient and a good starting point for subsequent calculations for large systems, but it fails qualitatively also when the fragments are strongly entangled. And at the same time, the last states that one obtains are a chemically intuitive basis for molecular Hamiltonian. And so one can set up this state interaction Hamiltonian that allows us to go beyond the mean field treatment of the interfragment excitation. And also one has control on the types of excitations that one can include. So here there are possible applications of the method. So one could study super exchange, or for example, modify the Hamiltonian to include spin-orbit coupling. And in principle, this is a method that one could think as being exascalable because of this fragmentation. So this is interesting, and doing this fragmentation method has attracted a lot of attention from the entire community. There are various approaches. I have described one of them in an extension, but the point is that I mean, when one goes from LASSCF to LASSSI, it means bringing back in the expansion some of the excitations that originally were not included. And so eventually one will eat again the exponential scaling. So how could we eventually proceed in a different way? And so here is where perhaps quantum computers could help us with this methodology. Again, let us think about this Pauline chains, which have important applications either in photovoltaics or molecular electronics, and where we have this alternating double and single bond. And as we said before, these are challenges for fragmentation methods, especially if we don't just look at ground state, but we look at excited states where these excitations are delocalized. So one could think, I mean, if we divide it up in these fragments where we have a double bond in each subspace, one could think about representing the orbitals in each subspace by using a quantum register. And for example, QP. And so this will basically be used to produce a last wave function on the register. And so in this particular case, what we have been exploring is to use the quantum phase estimation to collapse to the ground state of each subspace. But in principle, one could replace QPE by other solvers, eventually also classical algorithms. And then one could say, okay, if I just use QP, I basically solve the local wave function problems. But what about if I want to couple different fragments? And so what we've been exploring is to use unitary couple clusters to couple different fragments. And so the subspaces can select can be selectively coupled to each other unitary couple cluster by using unitary couple cluster. And in particular, in this first implementation that we have been following, the parameters for the unitary couple cluster were optimized using VQE. So let's see an example of this approach. So here the beauty is that one uses unitary couple cluster to couple the fragments that are in the last-wave function, but also uses the LAS as a better initial guess for the UCC VQE ansatz. So again, let's look at one of these systems. And here we are looking in particular at transbutadiene. So there are two double bonds here that we are breaking. Okay, so these are our two fragments. And so if one wants to study the full system with CAS-SCF, it would be a CAS-SCF 8 in 8. And the corresponding LAS is 4 in 4 on each fragment. So 4 in 4 times 2. And the orbitals are these pi, pi star, sigma, sigma star for each pairs, for each double bond. And the more we break the double bond, the more the multireference character increases. And these are the 4 localized orbitals in each of these subspace, in each fragment. So let's look with this approach, what do we get? So here we are reporting the dissociation of these two double bonds simultaneously in these systems. And so here we have the distance between each carbon and the other one in the fragment that remains still. And we report, okay, CAS-CI can be considered our reference value. If one just does LASSCF classically, in the original way, you see we are not describing correctly the system as dissociation, as we pointed out before. On the other hand, here we have also two other sets of data. One is this LAS UCC, and these are the black circles, and the other is UCC SD on the entire system. So the blue really is off. The other three seems pretty good. However, if we zoom in this region between 2 and 4, we see that actually this is the error of the methods with respect to CAS-CI, and we see that UCCSD performs not as well as our LAS UCC. So this is quite encouraging. So to summarize this part, it's useful to decompose wave functions in this chemically intuitive way, especially for these NISQ architectures. And LAS UCC is superior to classical LASSCF, but at the same time, it also outperforms conventional UCCSD, which is considered the workhorse of quantum computers. And so what we do here, we combine the fragmentation of the wave function, and we treat each fragment with QP, and then we use variational UCCSD to compute the total ground state energy by including this interfragment correlation. And so we take advantage of, in principle, one can take advantage of further developments in QP, VQE on top of these blocks. And even if, in this first implementation, we use QPE here and VQE in the interfragment part, we can replace them. So QPE can be replaced by another either quantum or classical solver, and as well UCC by different ansatz. And actually, we are looking into that at the moment.
That's a good question. So the
yes.
QPE here means that you want to solve the like local fragment exactly. Is that right?
Sorry, could you repeat the question? I couldn't hear you very well. Can you repeat again?
So the QPE part in this diagram that you showed means that you want to solve the local fragment, let's say exactly. Is that right?
Yeah.
And then after the QPE, you have some UCC to entangle them together. Is this the circuit structure?
Yes. So you use UCC to couple the fragments. Yes.
So the circuit, more specifically, because QPE has a success probability issue. So you would run the QPE, measure each block, make sure that it is successful, and then once all the blocks have succeeded, then you run the UCC. Is that correct?
Yes.
So if each block has a success probability P, and you have n blocks, the success probability will become P to the n. Is this going to be an issue?
Yes, it could be an issue. Yes, I have to say, I mean, so far we have only simulated all this on a classical computer, but yes, I think that your point is well taken. Yeah.
Thank you.
So far, what I told you is how to get good wave functions, strongly correlated wave function at an affordable cost. But when you want to compute energetics, the wave function is not enough. Before I showed you the case where if you just use your LASSCF to compute the J coupling, you were off significantly compared to experiments. So one is to do something on top of this wave function. And historically, people have, for example, done perturbation theory, second order on top of a CAS wave function. This gives the NEV-PT2 or CAS-PT2 wave function. But then on top of the cost of the wave function calculation, there is an extra scaling of several order of magnitude on top of that because you need higher order density matrices. So what we have worked on also in recent year is develop a new form of density functional theory called multi-configuration pair density functional theory. And the idea is to compute the total electronic energy starting from one of these multi-configuration calculation, which could be CAS, GAS, DMRG, or LAS. And so one starts from a multi-configurational wave function, and the energy is calculated using this expression where basically we have nuclear, the one electron energy, and the classical Coulombic electron-electron repulsion. And then there is this non-classical functional. So this could remind us of Conchamp. The difference is that here this non-classical functional, which we call it on-top functional, is a functional of the total density that comes from the multi-configuration wave function and the on-top pair density, which is a trace of the two-body density matrix. And so we basically from the MC calculation, what we get is this rho and pi, and then we use this expression to compute the energy. And here you can see, yes, the energy expression term by term. If we compare Conchamp DFT versus MC-PDFT, you see in Conchamp you have a single determinant. Here you have a CI expansion, and then there is the kinetic energy term where here you have the expectation value with this multi-configuration wave function. The nuclear attraction terms, the energy, the densities are different, the classical Coulombic repulsion, and then these two different, I mean, they are different functionals because it's a functional of rho from one determinant. Here you have a functional of rho and pi. And so to show you how this method performs, so this, for example, a data set, we are comparing, these are two very basic Conchamp functionals, PB and PB0. Of course, one can do better in the Conchamp world. But if we use the analogous, in our world, it's what we call translated PB, because we just take the same functional form from PB. And this is a typical wave function type of result. So PT2 on top of your CAS wave function. We see that our TBB is performing quite successfully, and you don't have to pay the extra price of the PT2 that you have to do in this case. So this really opens up to much larger systems, especially if you can control the cost of the parent wave function. And so we have used this pair density functional theory also in combination with these localized active space wave functions. And here it's an example where we have two so a bibenzyl, so there is a carbon-carbon single bond in between these two aromatic rings. And here you see, I mean, LASSCF is a good approximation to Cas. This is the error with respect to the corresponding Cas. And LASS-PDFT is a good approximation to the full Cas-PDFT. But here things are reasonably simple because, again, the two fragments are not strongly correlated. We also looked at the cis-trans isomerization of Stilbin, where instead between the two rings, there is a carbon-carbon double bond. And in this case, you see here we have the Cas and LASS curves for the S0 and T1 states. And here the Cas and PDFT curves for the two states. And you see, so LASS is not a very good approximation to Cas, especially here at 90 degrees, which is the more radical situation between the two. With pair density functional theory, the problem reduces significantly. So PDFT does a good job, even if it starts with this really poor wave function, but it's not perfect yet. So doing the SI or the last VQE seems to be a good option. And so eventually one could also envision doing the wave function calculations on the quantum computer and the pair DFT calculation on the classical computer. And this is actually what we have been working in collaboration with David Mazziotti. I had a last part of my talk in which I wanted to tell you a little bit about how we perform density matrix embedding theory on periodic systems, but I think now I am already at 44 minutes, so probably I want to skip this part to leave more time for questions. I will just conclude now by showing my acknowledgement slide, which is here. And so today I've talked about the work of Matthew Hermes for the LASS, and Ridish Pandahar and Abhishek for the LASS, and Hang Pham is the first one who developed periodic DMET, and especially the periodic work has been inspired by a lot of conversation with my colleague Giulia Galli, with whom it's really a pleasure to collaborate. And I would like to thank especially DOE for this work, and all of you for your attention.